Hello. In this episode, we're going to look at cathode ray tube experiment, where cathode rays are produced and studied to demonstrate that atoms are divisible. This was first demonstrated by JJ Thomson, and he won a Nobel Prize in 1906 for this experiment. And essentially, we will familiarize ourselves with the so-called cathode ray tube, which was very popular until very recently, because most people have this on their desks as computer monitors. Now they're being replaced by flat panel displays, and we will look at the exact experiment that was done in order to demonstrate that cathode rays can be produced under certain conditions. And then the experiment is also used to determine specific properties of the cathode rays. In fact, these are made of fast-moving electrons. And so this has been not known at that stage, of course, at that point. It's been established by this very experiment. And we will also examine how this discovery helped in understanding atomic structure in much greater detail. And we will design an experiment to measure the charge to mass ratio of cathode ray particles. And so, as mentioned, Thomson was awarded Nobel Prize in 1906 for this discovery. And here is a very simple apparatus that is shown from Wikipedia, a cathode ray tube. You may not have seen this on your desk, nevertheless. It's a vacuum tube where gas discharge, electric discharge through a gas, generates a beam of cathode rays, which, when impinged upon glass fluorescent screen, light is emitted. And this is because the particles are striking the phosphor on the glass, and the phosphor atoms and ions are excited to a higher state, and they emit light. And so this is a very cool picture of a classical cathode ray tube. And the specific parts of the cathode ray tube are shown here. It's the shape of a bulb, and in the base of the bulb is the cathode, is a positively charged material, metallic, and then at certain distance from it is the anode. But then there is an opening in the anode, so the emission from the cathode can pass through the anode. So by placing the anode at certain distance from that of the cathode and applying certain voltage across, we can create an electric field. If you created a strong enough electric field, and if the gas pressure is low enough, then the emission is observed from cathode. And that manifests itself as a beam that strikes the screen across the tube, and then the screen glows. And that's what you're seeing on the left-hand side. And so the red arrow representing the cathode ray. And these are called cathode rays because they're rays emitted by cathode. And they knew they are rays because these things moved in straight lines and were able to cast shadows. And so you can see clearly the shadow on the left-hand side of an object with the shape of a cross. And so they knew that the particles ought to be moving in straight lines. Particles themselves were not visible, but when they struck the gas particles, the gas inside would also emit. But when they hit the wall pasted with a phosphorescent material, the wall would glow. And so the screen on your cathode ray tube, if you had a CRT display on your computer desk, you would have noticed that there is an electron beam that is actually hitting the surface, and the phosphor is glowing. And so these cast dark shadows of solid objects, so we knew that they traveled in straight lines. And they're, depending on the gas, we are not able to change the properties of the cathode rays. Irrespective of the gas field, the same kind of rays were emitted. And so it was independent of the gas material. And also, it was initially thought that it is the cathode material that is emitting the light. Therefore, different kinds of cathode materials were used. As long as they're conducting metallic electrodes, they would give the same type of cathode ray emission. So they're also independent of the cathode material used. Therefore, it's been concluded that these particles could be emitted by any gas, and so must be present in all gases. All gaseous materials should have these kind of particles embedded in them. Furthermore, when we apply an electric field, these is deflected towards the positive electrode, and so therefore it's been concluded then particles must be negatively charged. So the application of electric field perpendicular to the beam deflects. So here you have a negative electrode on the top and a positive electrode on the bottom, and the length of this electrode is capital L, and then the beam is deflected towards the positive electrode shown by the green arrow, and the displacement can be readily observed on the screen by measuring the distance d with a ruler. So the particles travel through the applied electric field, the second applied electric field of length L, and then they are displaced by the distance d on the screen. So this can be visualized, and they are displaced towards the positive electrode. Therefore, they must be negatively charged. And then a magnetic field is applied to test the effect of the magnetic field on these particles. In fact, this is how your CRT screen used to work. It had several coils inside to generate magnetic field. Depending on what image it has to write on the screen, different amounts of current has passed through X, Y, Z coordinates of the magnetic fields, so the electron beam would move. And in addition to that, color monitors had 3 different kinds of phosphors, and so they had 3 different kinds of sets of coils to generate all 3 different colors associated with them. So it was a bit more complicated, but it was possible to generate different colors because of that. So a magnetic field is then applied to restore the electron beam back to its original. They will call electrons much later. So the cathode ray beam was brought back to its original position by applying a magnetic field. Then the magnetic field, in order to achieve that, had to be applied perpendicular to the electric field, also perpendicular to the path of the beam. Therefore, the magnetic field is interacting with the negatively charged particles. Negatively charged particles, if they are in motion, they generate a magnetic field. So that interacts with the applied field. And the applied field is exactly equal and opposite in direction to that of the particle field. Then it can be restored to its original position. And so that is being achieved by positioning the south-north perpendicular to the electrode and also the path of the cathode ray beam. So the diagram on the right hand side expands this and explains how the distance L corresponds to the path the particles travel through the applied electric field, and then they are displaced through a distance d on the screen. And the displacement in S is by the time they exit the electric field. That is the small s is the displacement. And so L is the distance the beam travels in the electric field. S, the displacement by the time the beam exits the electric field. And then D is the displacement noted on the screen. So these are the various variables. We pay attention to all these details because in the next slide we're going to use these quantities to obtain the charge to mass ratio of the particles consisting of the cathode rays, or composed of the cathode rays, or emanating from the cathode rays. So the math details are following. So we have the electron beam or the cathode ray beam exiting the electric field after passing through a distance L. The displacement by the time they exit the field is S, and by the time they hit the screen on the cathode ray tube, they have registered a displacement D. So by measuring the D and the strength of the electric field and the strength of the magnetic field that restores the beam back to its original position, we can calculate the E over M ratio. So when the electric field is applied, the force is equal to the field E multiplied by the charge on the particle small e. So this is standard from electric field theory. And so we start with a couple of different equations and integrate them. And so we'll do a little bit of math and a little bit of integration to figure out what are the characteristics of these particles. So we start with ds equals to v dt. This is from Newtonian mechanics. ds is the displacement s, differential of s, the displacement, is equals to v dt, the velocity times dt. This is classical mechanics. So if I now integrate on both sides of ds equals to v dt, yes, s, ds integral s, 0 to t, v dt. So v is the velocity. The velocity is not constant here, is not uniform. It depends on the temperature, on the time. As the particles spend more time in the electric field, the more force acting on them, and therefore they're accelerated. And just as an object falling through the gravity, field of gravity, is accelerated due to gravity. And so integral v dt, v cannot be integrated right now because it's a dependent, it also depends on time. And so now we write v equals to at, so that's by definition. And a is acceleration, t is the time. So now we can write this integral 0 to t a t dt. So now we have written the v in terms of time as function of time. And a, of course, is acceleration. Acceleration is uniform. As long as the electric field is constant, if you have a uniform electric field, then you have uniform acceleration. So then a is independent of time. So now we can integrate this. You get 1/2 a t squared. 0 to t are the 0 time versus time t. That's the time taken for the particle to travel through the electric field. And so 1/2 a t squared. And now we can write a in terms of force, because we don't measure a, we know force we are applying. So we can translate that into force. Force equals to mass times acceleration, or acceleration equals to force divided by mass. So I can now replace that equals to F over 2m t squared. Now we know force is equal to E times E. E is capital, the electric field strength, and charge on the particle E. So the product of these two is the force that we applied on the particles. So that is F. So now we can replace that. E times E over 2m t squared. And so now we have obtained a pretty reasonable relationship between S, the displacement that we have got in the experiment, and the time it takes for it to pass through, and the mass and the charge and the applied field. We still not have all the quantities we need to calculate, because we cannot measure t experimentally directly. It's hard. The time it takes for the particles to pass through, the distance is too short to be able to monitor it. So, but there is a way to obtain t by an indirect, in a clever method. So this is one of the reasons that Thomson made great progress in understanding what these particles are. Not just producing the particles, but being able to characterize them, obtain their specific properties. So the way then is E over M, charge to mass ratio. This is a very famous constant. We keep talking about this here also in anode ray particles and mass spectrometry, equals to 2s over ET squared. And so S can be measured experimentally by measuring D. D you can measure with a ruler on the screen. And so by knowing geometry, there are two right angle triangles. They're sharing the angle. So we can estimate S easily by geometry. So the only question is T. How do you measure T? This is a very clever way of measuring T. So what he has done, apply a magnetic field to restore the beam back to its original position. The magnetic field now is equal to B times E times V. That is, the B is the field strength, and electric field E generates certain force, and the magnetic field B generates an equivalent force, and we adjusting the field strength B, we can just neutralize the force due to the electric field. And the force due to the magnetic field is BeV, where B is the field strength, E is the charge, V is the velocity of the particles. And so when they are equal, we have EE equals to BeV, or V equals to E over B. So how does this help us? Well, this helps us because T is the length traveled, V is the velocity. So we can now write velocity in terms of charge, in terms of electric field strength and the magnetic field strengths. So then T equals to L, the length traveled in the field, times B over E. So once we have done that, T squared is then equal to L squared B squared over E squared. We can measure L, we can measure B, we can measure E, so we can measure T. That's the idea. So once you can measure T squared, you substitute that back into the expression we arrived earlier. And so now we can write E over M equals to 2S E squared over EB squared L squared, or equals to E over M equals to 2S E over B squared L squared. So we can measure S, we can measure E, we can measure B, we can measure L, therefore we can measure E over M. And a small note, how do you measure S? Using geometry. And this is a short assignment to figure out how this is to be done. As I mentioned before, the hint is there are two triangles formed by S and D that have 90 degrees, right angle triangles, also share the same angle on the top. So that's the hint. So from that we should be able to calculate value of S from D. So by measuring EB, L, and S, we can estimate E over M. And because these are later came to be known as electrons, we write them as E over M of electron. And so that is being experimentally determined to be a certain value in terms of coulombs per kilogram. So this is one of the fundamental foundations to demonstrate that all gases at that time, at least, have one specific kind of particle which has a charge to mass ratio equal to this. And this is universal for all kinds of gaseous materials. So then people have attempted to test if this is also the case with other materials and so on. Soon found to be that it's true that atoms in general have negatively charged particles with certain characteristic mass, where the charge to mass ratio is identical for all of them. So this immediately triggered further debate as to the nature of the atom. So in summary, the discovery cathode rays established that atoms can be divided. So this was a very important fundamental step toward understanding the structure of the atom. These particles, these rays are produced by electric discharge through gases at low pressures. Normally gases are insulators, so you need to pump them out to a certain low pressure and then apply a very high voltage to strike an arc or strike cathode ray emission. And we see these now in neon lights. This is a normal application of cathode ray tube experiment. The neon lights are descendants from the original cathode ray tubes. Cathode rays are also same as the beta rays, which are very much interesting and related in radioactivity. Natural radioactive materials emit beta rays, and they found beta rays are essentially the same as the cathode rays. Also, at that time, the thermionic emission means that if you take a metallic object and heat it to high temperatures, you produce particles, negatively charged particles, which are known to be the same as the cathode ray particles. And also, particles emitted by the photoelectric effect are also found to be exactly the same as the cathode ray particles. So, a number of different kinds of particles are now being identified to belong to the same category. They have been called electrons. So, use the cathode rays to determine the charged mass ratio by applying electric and magnetic fields and manipulating the experimental conditions. The ratio is independent of the gas chosen, E to M ratio, or the cathode material used. And so this appeared to be a fundamental particle making up the matter. And so it's a universal, negatively charged particle being named electron. Atom must also have, therefore, a positively charged particle to maintain its electron neutrality. And this then made predictions as to how to generate positively charged particles and study them. Problem set. Describe 3 examples of cathode ray tubes that are being used in daily life, or they were used in daily life. And some of them are still being used. And describe how you cannot produce 2 different kinds of cathode rays from the same gas or 2 different gas samples. Explain how you can show that photoelectrons and cathode rays are the same. Design an experiment. And you can send your responses as a PDF to the discussion board.